Hello everyone, good evening. My name is Amit Kumar Sharma, and as you know, every Friday we are having a live session for the course Energy Conservation and Waste Heat Recovery. And the course instructor for this course are Professor Pratap K.R. Das and Professor A. Bhattacharya from IIT Kharagpur. And I am the TA of this course. So as of now, we have covered up to week 6, and today we will cover week 7. So, as you all aware, every week we take a live session. In that session, we solve some sample assignment problems from previous years, so that this will be very helpful for you to understand the current year assignments and to understand how the problems can be like uh, can be uh, can be created from this course. Okay, so let's wait for another 5 minutes. After that, we will start. And this meeting is being recorded, and the recording will be shared with you, and this PPT will be also provided to you. Hello, Sehwaj. How are you?
Fine, sir. How are you, sir?
Yeah, fine. Are you in contact with the other class students?
No, sir.
Okay. Because from I think from last class only you are joining.
Yes, sir.
Yeah. Okay, let's wait for 1 more minute. After that, we will start. Okay. So let's start with a basic question, because you know that our previous week's classes were about heat pipes. So the first question is that heat pipes transport heat dominantly in 1D, 2D, 3D, and all of the above. So you have to tell that in which direction the heat pipes transport heat. Like maximum heat will be transported in which direction. So try to think and answer. Take 2 minutes. And you have to also think about the reasoning. What is the reason? Okay. For your hint, maybe I can draw a like simple heat pipes. So try to recall the structure. Maybe you can recall. So in heat pipe, one side there is a hot end. Other side there is a cold end. And there is a heat transfer from hot end to cold end. So any answer? Shahbaz?
Sir, all of the above, sir.
Okay, all of the above. Okay. Maybe you can rethink, because the question is that heat pipes transport heat dominantly. So dominantly there will be only one direction, because dominants mean that, like, suppose if the complete heat transfer is 100%, so maybe 95% is only in one direction and remaining 2-3% in other direction. And if you see this schematic of the heat pipe, sorry, schematic of the heat pipe, then maybe you can assume, maybe take another 30 seconds. Try to remember the class notes. I have also given you a hint. Okay, any answer? Okay, so the correct answer is answer A. Okay, so dominantly the heat transport in heat pipes will be in one direction only, 1D. That's why they are famous, because the axial thermal conductivity is very high in heat pipes. So the axial thermal conductivity is very high. So it is about in the range of 1000 watt per meter Kelvin. Okay. So the axial thermal conductivity is very high in heat pipes compared to the transverse thermal conductivity. Transverse mean other directions. Okay. Also, the dimension of pipe in axial direction is much higher compared to other dimension. So this is also a reason. Like, suppose I have already shown you the schematic diagram like this. So the heat will be mostly transported in one dimension, in axial direction. So this is the reason why that axial thermal conductivity is very high in heat pipes compared to the transverse this thermal conductivity. Also, the dimension of pipe is in axial direction is much higher compared to other dimensions. Okay, so because the axial length will be very high and the transverse like dimension is this, so the dia is not like very thick, because the transverse direction will be this, so the thickness is not so high, only very, you can say, very thin sides are there. So the dimension of pipe in transverse direction is not so high. This is also a reason. So the correct answer is A. Heat pipes transport heat dominantly in 1D direction, one dimension. So that is axial direction. Okay. Let's move to the other question. The question number 2 is heat pipe act as a. So we have 4 options: active heat transportation device, passive heat transportation device, semi-active heat transportation device, and none of the above. You have to answer like which type of heat transportation device is heat pipes. So let 2 minutes and let me know the answer. Any answer?
Sir, passive heat transportation device.
Okay, and what is the reason? Like, what is the reasoning for your answer? Like, what is the difference between active and passive? Because if you are saying a answer, then you should know what is the difference between active heat transportation and passive heat transportation. Take 1 more minute to think about it. Because suppose in one heat transfer, we have seen like we require some power source, and one heat transfer, we does not require any power source. So do in heat pipes, we require a power source?
No, sir.
Okay. So you are saying the heat pipes act as a passive heat transportation device. So what does it mean? I have given you a good hint. You can answer, I think. Okay. So as you told that heat pipes are not having any external power source. Okay. So that's why they are passive heat transportation device. In active heat transportation device, we have to use some external power source for the heat transportation, like a pump. Okay. In which suppose we are pumping the condensate back to the evaporator. So heat pipe does not need any external power to pump the condensate back to the evaporator. Hence, it is passively operating device. So there is no actively involving power source. Okay. Difference in one heat transfer, we need an external power that is active, and in passive, we don't need any external power. So the heat pipe act as a passive heat transportation device. So the correct answer is answer B. Question number 3 is, which of the following orientation of the heat pipe is preferred to attain maximum performance? So option A is vertical with bottom evaporator and top condenser, horizontal, inclined with bottom evaporator and top condenser, inclined with top evaporator and bottom condenser. It's a very good question, and I think in one of the class there is complete calculation also for this. I think in lecture number in this week's third lecture or fourth, I think there's a complete calculation to show that what is the effect of inclination. Okay. Maybe you can maybe I can give you a hint. Suppose this is a heat pipe, so it is inclined on an angle alpha, suppose. So the professor has derived a complete relation with the heat transfer of this alpha. Okay. From that you can understand that which position is better for the heat pipe. So take 2 minutes to answer it and come up with a good reasoning. Any answer? Any answers, Sahbaz? What do you think?
Sir, vertical with bottom evaporator and top condenser.
Okay, and what is the reasoning?
Sir, heat flows from the hot forms from bottom to top, no, sir.
So this is the suppose heat pipe. Okay. So you are saying that vertical with bottom evaporator and top condenser. So the condenser is here. And this is the evaporator. Okay. So you are saying that heat will be What were you saying?
Heat flows from bottom to top.
Okay. Then heat flow from like this. Okay. But what is the benefit? What is the benefit in putting like this? Because one end is hot end and one end is cold end. So heat will
Yes,
flow.
sir.
If your heat pipe is suppose like horizontal, then also heat will flow. But what will change when you put it vertical? Like in our laptops, you can see we are having heat pipes. So they are in only horizontal direction. But still they are cooling the laptop, okay? But the heat transfer is not maximum. The maximum will be on vertical with bottom evaporator and top condenser. But what is the reason for that? So the reason is that gravity is playing role, okay? Because from condenser, liquid is coming back to the evaporator side, and if it is vertical, so they can easily come under gravity. They don't have to move against the gravity. So the pressure due to hydrostatic head assist pumping effect in moving the liquid from condenser to evaporator. So this is the reasoning. For detailed explanation, you can refer to the class notes. I think in class video, in class notes, professor have derived a very long relation of the heat transfer with the inclination angle. So the main reason is that pressure difference due to hydrostatic heads assist pumping effect in moving the liquid from condenser to evaporator, because the liquid droplets can easily come downward, because this will be the direction of gravity. If suppose we put it like in inverted position, now the condenser at bottom and the evaporator at top. Now what will happen? The liquid have to go upside. Now the gravity will work on the liquid droplets against the motion. So the gravity will resist, and in this way, uh, the flow will decrease. Okay, and the result will be the performance will decrease. The heat transfer performance will decrease. So the correct answer is vertical with bottom evaporator and top condenser, because the pressure difference due to hydrostatic head assist pumping effect in moving the liquid from condenser to evaporator. Okay. Okay. Question number 4. Capillary pressure head must be greater than. So we are talking about capillary pressure head. The options are sum of liquid pressure drop in the wick and vapor pressure drop, sum of vapor pressure drop and hydrostatic pressure head, sum of liquid pressure drop in the wick and hydrostatic pressure head, sum of liquid pressure drop in the wick, vapor pressure drop and hydrostatic pressure head. So take 2 minutes to answer. This is also linked to the previous question. First of all, you have to think about like what is the meaning of capillary in heat pipes. Any answer?
Sir, these are sum of liquid pressure drop, the weak plus vapor pressure drop and hydrostatic pressure. Because there is a formula, sir, derivation capillary delta PPC is equal, greater than or equal to delta PL plus delta P low PG. Formula is there, sir. Direct
Yeah.
formula.
And what is the like the formula is there or what is the concept? What is the meaning
Summation
of like what is
summation
the
of
meaning of okay, summation of I got your point, but what is the meaning of this capillary pressure head? Why it should be greater than this all summation? Suppose if it is not greater than, then what will happen? The point is that suppose it is not greater than, then what will happen? Think about it. Try to recall like the idea of evaporator and condenser. Like evaporator is working at this hot end and the condenser is working at cold end. And what is the role of this wick? What is the wick doing actually? Any idea?
No, sir.
Okay. So the capillary pressure head must be greater than. So the wick is, what is the wick doing? Basically, wick is transporting the liquid droplets from the cold end to the hot end. Okay. So basically, the wick is transporting the liquid droplets because the cold end to the hot end. At hot end, the liquid again convert to the vapor, and vapor will travel to the cold end. Then this vapor at high temperature will give heat to the liquid, will release its heat. Okay, again become in liquid form. Okay, and again this liquid will be, the liquid droplets will goes to the wick, and wick will, using the capillary action, transport this liquid to the hot end, and again from hot end the liquid will absorb heat from the outside, again will become vapor. In this way this heat pipe works actually. Okay, now if the capillary pressure is not enough, if the capillary pressure head is not enough, then what will happen? Then this wick will be not able to transfer the complete liquid droplets to hot end. Okay, so the wick will be not able to transfer the liquid droplets to hot end. Okay, in this way the performance will be dropped. So to eliminate this issue, this capillary pressure head must be greater than the sum of liquid pressure drop, because there is a liquid pressure drop head. Okay, due to hot end and cold end, because there is uh, different liquid at each end, so there will be difference of liquid pressure drop. Okay, vapor pressure drop is also there, and the hydrostatic pressure head due to the gravity. So considering all these three heads, so the capillary head should be greater than the sum of all these three heads. After that only the liquid droplets can be travel back from cold end to hot end using capillary action. So this is the reason. Okay. For complete detail or for more detail, you can refer to the class notes. There is a whole derivation regarding this. Okay, so it's a very important question. So the correct answer is option D. Question number 5 is, how bends along the length of the heat pipe impact functioning of heat pipes? So there are suppose bends on the length of heat pipe, then how they are affecting the heat pipe? So the option A is, power rating remains constant as long as length is unchanged. Option B is, power rating reduces. Option C is, sharp bends provide additional pumping force. Option D is, complex dependence on overall geometry and fluid thermophysical properties. So take 2 minutes and let me know the answer. Any idea? Any idea about the answer? Like, suppose if there is a bend, then what is happening? For a hint, the answer is linked to the previous question. Think in that perspective. Like in previous question, we have discussed about like pressure heads and everything. So think with that mindset. Suppose this is a heat pipe, okay? So there is a bend. What will happen? Try to think, try to relate with the previous question. Okay, so tell me what will be the effect on pressure heads?
Pressure is going to reduce, sir, at that.
Okay, so pressure will reduce, then what will happen? What will be effect of that on the capillary pressure head?
Power rating is reduces.
Yeah, correct. Because the capillary action will not good as that was good in the straight configuration. Okay, so the bends in the flow path will result in additional pressure drop. So there is additional pressure drop because if there is a straight pipe, then we can see that there are three pressure drop. Okay, like in previous question we have seen like liquid pressure drop, in the wick vapor pressure drop, and hydrostatic pressure head. So these three are for a simple case. So suppose a straight heat pipe, but if there is a bend also, then due to this bend, this pressure head will further increase. So if this pressure head will further increase, and then capillary pressure head, suppose this value, suppose 10, just assume any 10, okay, and this summation is suppose 7. So this 10 is greater than 7. Okay. So for this condition, the capillary pressure head is like 10 and this is 7. So there is difference of plus 3. So the capillary action will be there and the heat performance will be good. But now if there is a bend also, now what will happen? This 7 will increase to 9, maybe 8 or 9. Okay. Because this will increase because due to bend, there will more pressure drop. So this will increase. So, but still the capillary pressure head will remain 10. Then this will reduce the performance. Okay. So the power rating will reduce. So bends in the flow path will result in additional pressure drop, resulting in lower flow rate and power rating. So flow rate will also reduce and the power rating will also reduce. The correct answer is answer B. Okay. Question number 6. Which of the following is oblique are the feature or features of vapor chamber? Option A is 2D heat dissipation, similar working principle as heat pipe, passively operating nature, and all of the above. Take 2 minutes to answer. I think we are having two students. I think Prashant, are you there? Okay. Okay, any answer from Sehbaz or Prashant?
Sir, D, sir, D is the right answer, sir. All of this. These are the futures of vapor chambers.
Okay. So there will be 2D heat dissipation, similar working principle as heat pipe.
Yes,
So
sir.
and passively operating nature.
Yes, sir.
Okay, let's see. Yeah, correct. The answer is D because unlike heat pipe, vapor chamber dissipate heat in linear direction and has similar working principle as that of heat pipe. So it will be in 2D heat dissipation. Otherwise, it is similar to heat pipe and also does not require any power source. So it will be passively operating nature. Okay. So all three conditions are there for a vapor chamber. So the correct answer is D. Question number 7. Which of the following generate power in thermoelectric generator? Option A is pressure gradient. Option B, concentration gradient. Option C, temperature gradient. Option D,
C,
none
sir.
of the above.
C, sir,
Okay,
temperature gradient.
very quick. Let's wait for 1 minute at least. And what is the reasoning? Try to think the reasoning. Like if there is just you are saying the temperature gradient. So what will with changes in the materials due to temperature gradient and there is heat, there is the heat energy will be converted into electrical energy. So what is the reasoning behind that? Okay. Now, Sebas, you can tell your reasoning. What is the reasoning behind this? Anyone? I think we have an answer temperature gradient, but what is happening there due to this?
Sir, by high temperature, electricity is going to generate, sir.
How? How?
Sir, transfer of energy takes place, sir. First, thermal is to mechanical, then mechanical into electrical is conversion of take place.
Okay. I think you are going in wrong direction, I think. It's TEG. TEG, thermoelectric generator. So the meaning of the basic of this is that thermal to electrical. That is the main concept. There is no mechanical part. So the direct heat energy will be converted into electrical energy. So we are eliminating the mechanical part. Okay. So that is the main concept here for TEG, thermoelectric generator. So here we are using the thermal energy like heat to directly convert into electricity. There is no mechanical part. Now I think you can rethink your answer. Your answer is correct. It's temperature gradient only. But what is happening there? So this is your hot end and this is your cold end. Okay. What is happening here? Suppose in between there should be something. Then what is happening there? Due to high temperature. So what is the main reason, like we are talking about electricity? So what is the main, like main part of any electric current? What is the main reason behind this? Who is responsible for an electric current? Any idea? Like electron, proton, neutron, who is responsible for electric current?
Electrons, sir.
Electron. So if there is electric current, then there should be flow of electrons. So now you know one thing, that there should be flow of electron. So you are having heat and you need to flow the electron. Then how can this be possible with temperature gradient? What do you think? So due to temperature gradient, the electron of a metal will take energy and they will jump from their state to other state and they will travel. Okay. So if the electrons are traveling, then current is flowing. This is a very basic definition. And for more detail, you can read in detail about Seebeck effect. So in thermoelectric generator, power is generated due to temperature gradient at the junction of two dissimilar metals. So we have to contact two dissimilar metals. One will be at hot end, one will be at the cold end. Okay. Then there will be result of an EMF, electromotive force, due to Seebeck effect. For more detail, you can refer to the class notes, but basically the electron will get energy at hot end and they will be excited and they will travel to the other side, okay, on the cold side in this way. And from the place from where they jump, so there will be creation of hole, so another electron will come to that and again this cycle will move on, and in this way we will get electric current. So this is the reason. So there is no mechanical power. Okay. So directly thermal energy is converted into electrical energy. So that is the thermoelectric generator. Okay. I think it's clear. So yeah, it's a genuine doubt. Anybody can think because thermal to mechanical to electrical. It's genuine doubt, but it's good that it's clear now. Okay. So you have to remember that thermoelectric, the efficiency is very low. Efficiency is very low. It's around only 10% to 15%. Okay. That's why we cannot use thermoelectric generator for large applications, but still, suppose there are some waste heat available on those locations, we can use it. Okay. And at IIT Delhi, many of my colleagues are developing thermoelectric cook stoves. Okay, so what they are doing actually in rural areas, you know that there are lack of electricity. Okay, but they are still cooking. So they are putting this small TEG device on their cook stoves. So what they are doing, they are converting the heat of the cook stove into electricity, and they can use this electricity to charge their mobile phones, to charge their other electronic devices, or to light a small bulb and etc. Okay, so it's a very good initiative. So TEG is very good for waste heat recovery. Question number 8. In thermoelectric device, the thermoelectric elements are connected to each other in series according to electrical connection, in parallel according to thermal connection, both of the above, none of the above. Take 2 minutes to answer. You have to think about the class notes. Any idea? The question is electric device. The thermoelectric elements are connected to each other in series according to electrical connection, in parallel according to thermal connection. Both of the above, none of the above.
Sir, series according to electrical connection.
So saying option C, in series according to electrical and in parallel according to thermal. What is your reasoning? Any idea? Anything? Okay. So the correct answer is C. Okay. And the reasoning is that as the N and P type semiconductors of a single pair are joined, and one end and hence creates a series type connection electrically. So when we are connecting these N and P type, so in electrical point of view, they make series connection. However, the ends of the P and N type semiconductors of a single pair are maintained at a single temperature and hence result in parallel thermal connection. So if you see from the point of view of thermal, then they are maintained at same temperature. So that will be a parallel configuration. But you know that we want more voltage, okay, more current, then it should be in series, okay, in series according to electrical connection. So because the N and P type semiconductors of a single pair are joined and one end and hence creates a series type connection electrically. However, the ends of the P and N type semiconductors of a single pair are maintained at a single temperature and hence result in parallel thermal connection. So the correct answer is C. So question number 9. If the liquid mass flow rate in a heat pipe is found to be 0.02 gram per second, calculate the axial power rating. A 12.5, B 20.5, C 45, D 32.5. So let me know the answer. I think you have to use about some value of enthalpy for liquid. So we are talking about heat pipe, and in heat pipe, you know that there are vapor and liquid both. You have to use enthalpy, and which enthalpy you have to use? I think it's HFG. So try to find the HFG of liquid and let me know the answer. Any idea? I have given you a very big hint about HFG. Are you calculating, Sahbaz?
No, sir. How to calculate?
Okay. Okay, it's very simple actually. So you know the HFG for water is 2250 kilojoule per kg. Okay. it's obvious that the fluid here is water. We have considered water here. I have also mentioned in our hint. Okay, so you can find out this value. The axial power will be the mass you have given into HFG, 45 volt power. Okay, so because this is the enthalpy, this is the flow rate, so the power rating will be this. So 45 watt heat you can transfer from that heat pipe with this flow rate using water as a liquid. Okay, so also another hint you can see like the answer in watts. Okay, you have given gram per second, so you know that I have given you a hint like enthalpy. So enthalpy is in kilojoule per kg, and you have other unit in gram per second. From units also you can find out that you have to just multiply it. Because after you multiply kilojoule and convert this kg to gram, 1000 gram into gram per second, this will cut out, and kilojoule per second will convert into kilo to again convert it 1000. So it will also cancel out. So joule per second will be watt. So in this way also with the unit balance also you can find out like how to solve the question. Okay. So unit balance is also very important part. You have to remember like what are the units for given data and what is the unit of the answer. You have to do the unit balance also. It's very important. Question number 10. In a heat pipe in horizontal orientation, the length is reduced by 50% while the original fluid is replaced with an alternate fluid having half the viscosity and density. What will be the change in the power rating? Approximate. Increase by 42%, reduction by 50%, increase a factor of 2.8 and double. So you have to find out that what will be the change in power rating if you are changing the fluid. So take 2 minutes to think about it. Let me know the answer. So focus should be on the half the viscosity and density. try to think the answer with the viscosity and density and length. Any idea? Try to apply some basic mathematics. Okay. So from our analysis, we can see that mass flow rate is directly proportional to density and inversely proportional to effective length and viscosity. So from the derivation, okay, for that you can refer to the class note. So the result is that mass flow rate is directly proportional to the density and inversely proportional to the effective length or viscosity. So now here we have mentioned that the fluid having half the viscosity and density and length is reduced by 50%. So what will happen? Therefore, all the changes stated in the problem, the power rating will increase by 1 by half, so 50%, because they are reducing the they are like length is also reduced to 50%, okay, and the viscosity and density is also reduced to 50%, so that the power rating will, because it is directly the mass flow rate is directly proportional to the density, so mass flow rate will change, and due to mass flow rate, as or in previous question, the power rating is HFG into mass flow rate. So it is depending on mass flow rate. So mass flow rate will be basically double. Okay. So in this way, the rating will increase by 50%. So therefore, for all the changes, the power rating will increase by 50%. The closest numerical answer is option D. Will be doubled. Okay. Let's. So now I think our questions, we have seen 10 questions for previous assignments. Now it's time to discuss some, or you can say revise some basic concept about heat pump. Today we have solved various questions for heat pipe. So in this diagram, you can see this is the condenser, this is the evaporator. So here is the heat in, you can see there is the heat out, okay, and there is the wick, okay, and the outer part is insulated. So you can see the heat is coming in. So the liquid droplet, you can see this is the blue arrows are representing the liquid and red arrows representing the high temperature steam. So you can see the steam is coming here and converting into liquid, heat is going out, and again liquid is flowing back to the hot side. In this way, the heat pipes are working. So this is the direction of the vapor flow, is the direction of water, okay. So this is an example of heat pipe. So basically this is the thermodynamic cycle, the ideal thermodynamic cycle for heat pipe. So it is a TS diagram, okay. So the process 1 to 2 is heat applied to the evaporator through external sources, vaporize working fluid to a saturated state 2 days, this one, or superheated state or vapor state at 2. From 1, where the liquid is taking heat from the external source, and converting into either 2 days or 2. You can see this phase. This is process, first process 1 to 2. After that, in 2 to 3, vapor pressure drives vapor through adiabatic section to the condenser. So due to the vapor pressure, the vapors are driving through the condenser side. They are going to the condenser side. So 3 to 4, vapor condenses, releasing heat to a heat sink. So now vapor is converting into liquid. In this way, in this, they are taking Q in here, it's Q out. Okay, now the 4 to 1, now at 4, the vapor converted into liquid at the condenser end, but now we have to supply it back to the evaporator end. So it will be through the capillary action. Okay, so the capillary pressure created by the in the wick pumps condensed fluid into a evaporator section. 4 to 1 will be the capillary action, okay, from the wick. In this way, the complete TS diagram is shown here. So this is condenser, this is evaporator, this is adiabatic section, and this is the wick. Okay, so basically 1 to 2, Q in, then Q out. Any questions, Savas?
Sir, no problem, sir. Only 10 problems only.
Sorry?
Only 10 questions only, sir. No more questions.
Yeah. Today we are having only 10.
Okay, sir.
So this is the concept for idle thermodynamic cycle. Now, what are the advantages of heat pipe? So the advantage of heat pipe is that very high thermal conductivity. So effective axial conductivity is around 10,000 watt per meter Kelvin. Very high thermal conductivity. They are light, reliable, and cheap. They're very cheap, very reliable, and very lightweight. Means of transporting heat from point A, like in inconvenient location, to point B, that is convenient location with minimum thermal resistance. So the best example is laptop. Okay, so in laptops, in our motherboards, we are having different like our processor and graphics card and different devices on different locations, but we can have only a you can say the exhaust either on the left hand or right hand side. Okay, so by means of heat pipes, we can configure the heat transfer, okay, through the processor to the exhaust. So from inconvenient location to the convenient location with the minimum thermal resistance. So this is again a more detailed diagram where you can see everything in detail. So this is a heat pipe. Okay. So here you see the heat in. You can see the heat in. Okay. Here you can see the heat out. And how this heat in and heat out is happening? That is happening from this liquid flow. Liquid is flowing by the help of this wick structure. Okay. This is the vapor flow. Vapor is going from hot end to the cold end, then through the wick, it's converting back into the liquid by releasing its heat out, and the wick is transporting back the liquid to the hot end, and this is again converting into the vapor, and again the same cycle. So this is the heat pipe. Anybody having any doubt in this structure, in the working principle? Let me know. We can discuss. Anybody? Sabaj?
No, sir.
Okay. I think Mr. Prashant, are you there? Today we are having two participants. Mr. Prashant? Okay, he is not responding. Okay. So I think there is no doubt in this. So what are the best application for the heat pipes? So the best application for the heat pipes are gas to gas heat recovery. So it's very easy for gas to gas heat recoveries. Okay. So we can install, like in here you can see the multiple heat pipes are installed, like 1, 2, 3, and multiple. Okay. So there are n number of heat pipes. Okay. One side there are hot gas, and the other side there is cool air. Okay. One side the cold air is going, and the other side the hot west gas is incoming. So in this way, we can heat the cold air to heated air for our process. Like suppose in a process we require some heated air, then we can apply the gas to gas heat recovery system. We can apply the heat pipes, and we can use the west hot gas heat to heat up the cold air. So the heated air can be used in our processes, and this the the waste heat that was available with the hot waste gas can be recovered. Okay, so this is the best example, and you can see the simplicity. You just have to install the heat pipe. There is no external power is required. There is no like handling of liquid like in our other heat exchangers and all. So it's a very simple system. Okay, and we also know the heat pipes are very reliable. They are very cheap. So it is very easy to install these. It is easy to use these. So that's why it is very best to use for gas to gas recovery to exhaust gases. Other application is de-icing. So de-icing is also a very good application, because in foreign countries where the temperature are where the temperature during winter is around -10, -5, -20. Okay. So on those locations on the road there will be huge layer of ice. Okay. And if the ice is there, then you cannot drive vehicle on the road. And if you are driving, then there is a like very high chance of accident. Okay. Your vehicle will slip on the road because there will be no friction. So in that case, what we can do, you can see here, we can install heat pipes. So this is the ground. This is the ground of the road. This is the earth crust. Okay. So we can install some heat pipes underground. Okay. So in this case, the part of heat pipe that is just underneath the ground. Okay. That will act as the evaporator or condenser. What do you think? What do you think, Sabaj?
Sir, one second question.
Sorry.
One second question, sir.
Okay. So we have to do de-icing. Okay. So this is a pilot study in some country. Okay, so here you can see this is the ground level. Okay, the level of the road. Okay, on the underground we are installing a heat pipe. So this is a one section. This is more deeper in the underground. This is section. So this is a complete heat pipe. So basically, we want to use the bottom heat to supply it on this side so that the ice will be melted and there will be no ice on the surface. You can see the example on this area of road. Underground heat pipes are installed, so you can see there is no ice, but on this side no heat pipe, so there is ice. So which end is the condenser and which end is the evaporator?
Top one will be the evaporator, sir, and bottom will be the condenser.
You are saying this one will be the evaporator.
Yes, sir.
And this one will be the condenser.
Condenser.
So what is happening in the evaporator? What is the evaporator doing?
Heating, sir. Heating the pipe.
Heating the pipe.
So that the ice upon the surface going to melt, sir.
Okay. Yeah, this is a very good question. I am giving you again 2 minutes to think about it. Like this is the heat pipe, okay? At the one end, we are doing heating, and on the other side, we are doing
Cooling.
cooling. And there is a medium fluid. Okay? Now take 2 minutes again, think thoroughly. It's a very good question, very conceptual question. Okay? So there is a condition that you have to melt the ice. You have to melt the ice of the rod, and which end should be like condenser or evaporator? Now take 2 minutes thoroughly and tell me the answer with reasoning.
Sir, bottom will be the condenser, sir. Bottom will be the evaporator, sir.
Okay,
Because
but earlier you were saying that bottom will be the condenser.
no, sir, because the supplies from bottom to top the hold by the surface, it is going to convert to the condenser. Again, it is going to heat.
So you are saying that the bottom should be the, let me write in a different color, because earlier you were telling that it should be condenser. Now you are saying it should be the evaporator. Okay.
Yes, sir. Because
Yeah. Why?
cold
Because
condenser supply of water comes down, sir, after heating. Again, it has
okay.
to supply heat.
Okay.
Again, it will going to evaporator. Cyclic process, sir.
So earlier it was not cyclic. Like in earlier answer, suppose if I change it, if I made it condenser, then what will happen?
Both will be condenser. Top and bottom will going to condense. No evaporation going to form.
No, no.
No removal of ice takes place from the surface, sir.
Why?
Because both will act on the surface is a cold now, sir. There will be
Yeah.
no heat.
Okay.
So there will be no melting of ice takes place on the
Okay.
surface.
So basically you are saying that the top part should be, it should be condenser.
Yes, sir.
So if this is the condenser, then how the ice will be melt? How the ice will melt?
Sir, it changes to cold now, sir. Cooling place takes place by the before only it will be in evaporator. By the climatic condition of the surface, it goes to condenser, sir.
No, no. If this is the condenser, Then how the ice is melting? I'm asking that. Because in you can see in condenser, what we are doing cooling. So we are doing cooling in condenser, and you are saying with by the cooling, the ice will melt. How the ice will melt by the cooling? The question is that how the ice is going to melt with the cooling, because we are doing cooling in the condenser and heating in the evaporator. What do you think, Sahbaz?
Sir, I'm in confusion, sir. No.
Confusion? Yeah, that's why I'm asking, because I know you will confuse. Am I right? Because what
Sir,
we are doing
right, sir.
in condenser we are doing cooling.
Yes, sir.
But how the cooling is melting the ice? The point is that if you are doing cooling, how will ice melt? Because for ice to melt, you should do the heating.
Sir, evaporator supplies he supplied it heat, sir. By that heat of the surface temperature, surface coolness, it is going to condense.
So what is this heating and cooling? What this heating and cooling means? Just tell me that thing. When I am saying that we are heating at the evaporator and we are cooling at the condenser. So on which context I am talking about this heating and cooling? For in which context I am talking about this?
Heat pipe only, no, sir.
Yeah, heat pipe, I know heat pipe I'm talking, but am I talking about the external surface or I'm talking about the fluid? The point is that then only your confusion will clear. When I'm saying that we are doing heating at the evaporator and cooling at the condenser.
I think, sir, the entire it should be evaporator by that coldness. It is going to up the top, bottom. It is going to condense. Again, after getting the condensed climatic condition in the pipe, again it is going to evaporate. Again, start heating.
No, you are not. You are confused actually. Just answer this first actually. After that, your confusion will clear. When I'm talking about like we are doing heating at the evaporator and cooling at the condenser, and the water is converting into steam at the evaporator and liquid at the condenser. So, which heating and cooling I'm talking about? For which heating?
De-icing.
Sorry? No.
No.
For heat pump. So basically, I am talking about the fluid actually. You have to think about that. When I'm saying the heating at the evaporator end, so I'm talking about the heating of the fluid. Okay? Which heating? Heating of the fluid. And when I'm talking about the cooling at the condenser end, so I'm cooling of the fluid. Okay? Because the cooling is taking place of the water, because water is in vapor state, and vapor state, if the cooling is happening, what is the meaning? That then water vapor is releasing its heat. So what will happen? Then this is the your heat pipe. Then this end you will absorb heat, and this end you will release heat. So basically, at the condenser end, you will be releasing heat. Okay, Q out will be there, and at the evaporator, Q in will be there. So if you want to melt the ice, there should be heat available. So Q out should be there. Okay, because the heat will go from the heat pipe to the outside environment. That heat only will melt the ice. So this end should be the condenser, and this end should be evaporator. Okay, because the earth crust, as we go the deeper, the temperature will more. So the liquid will absorb the heat from the Earth's crust underground, okay, and convert it into the vapor, and the vapor will flow to the condenser. And here, as the outer temperature is very cold, so that will release the heat to the ambient, and the ice will melt, and again the liquid will come back to the evaporator. So this is the funda. Okay. When I'm talking about heating at the evaporator, it means I'm talking about the heating of fluid. When I'm saying cooling at the condenser, it means I am talking about the cooling of the fluid. Okay. But basically at the condenser side, if you see in the perspective of heat input and heat output, then on the condenser side, there is always Q out. So for melting the ice, you need Q out. There should be Q out from the heat pipe. I think now it's clear. Is it okay? Sebaz, is it clear to you?
Yes, sir. Yes, sir.
Yeah. So don't confuse in the heating and cooling, because that's why I was talking about heating and cooling only. Because when you think about like cooling at the condenser end, but how the ice will melt by the cooling. So I'm not talking about cooling, the overall cooling. I'm talking about the cooling of the condensate. That is the main funda. So another application of heat pipe is in IC engine and gas turbine plant. So in IC engine, you can see we can put a heat pipe, so the exhaust air can heat the input gasoline, and this can improve the combustion in carburetor. On the other side, in gas turbine, we can use heat pipe, and we can like use the exhaust gas heat to heat the inlet of the air. Okay, in this way, we can use the heat pipe applications. And this is the wick structure. So there are different types of wicks available. Wick structure are available. Okay, the first is a screen type, then centered, and then this grooved. So this is, you can see the axial grooves. Okay, so different type of structure have different types of performance. So these are available structure. This groove one is very popular. So this is the basic example of, you can see the heat pipes. Okay, so here suppose a processor, and here is another like IC that required cooling. So we can install heat pipe, and here is the exhaust. So tell me which part is the condenser and which part is the evaporator. This is part, suppose part A, and this section is part B. Now tell me, Saibaz, tell me anyone else who is in the meeting, which part, like A is condenser or evaporator, or B is condenser or evaporator. Take 2 minutes to think and tell me the answer. Any idea?
Sir, A is the condensing, B is the evaporator.
A is the condenser and B is the evaporator. Okay. From B side, the heat will be going in and A will release the heat to the surrounding. So it will be Q out, it will be Q in. So yeah, now it's clear to you. And I think it will
Yes,
be
sir.
clear to everyone else. Yeah. So this is the funda basically, where the Q in will be there, that will be the evaporator, where the Q out is there, that will be the condenser. So again, a CPU solution in laptops, heat pipe. So you can see this is the heat extraction, it's the heat rejection. So it is the evaporator, and this is the condenser. So there are some limitation when heat transfer limitation are there. One is the capillary limit. It occurs when the capillary pressure is too low to provide enough liquid to the evaporator from the condenser. So it leads to dry out in the evaporator. So these are related to our today's questions. Okay. So dry out prevents the thermodynamic cycle from continuing and the heat pipe no longer function properly. It's very important. So the capillary limit should be there. So the capillary pressure drop should be more than the pressure drop of static, the hydrostatic head, and the vapor pressure head. Another one was what? That question, I think that was, yeah, liquid pressure drop, vapor pressure drop, and the hydrostatic pressure head. Okay. And the second one is boiling limit. So it occurs when the radial heat flux into the heat pipe causes the liquid in the wick to boil and evaporate, causing dry out. So it should be also note there boiling limit occurs when the radial heat flux. So radial heat flux would be very low into the heat pipe, cause the liquid in the wick to boil and evaporate, causing the dry out. So suppose this is the heat pipe. Okay. And suppose the water is like coming from here, this side, from the wick. And suppose the radial heat flux is very high, U in. Then what will happen? This water will not reach up to the this end, evaporator end. Okay. I think Sebas, your microphone is on actually. Yeah.
Sorry,
So,
sir. Sorry.
yeah. So this you can see the liquid will coming to the evaporator end, but as you can see that the radial heat flux is high. So what will happen? This liquid droplets will convert it into vapor in between. Okay. And they will not reach up to the evaporator end. If they are not reaching up to the evaporator end, then they are not able to absorb the heat from the main end, that where we require the heat absorption. Okay. So in this way, it will be dry out. It is called dry out. So there is no liquid available at the evaporator end, and there is no liquid available to absorb the heat from this end. So the heat pipe will fail. So we have to check also the boiling limit. Then there is entertainment limit, a very weird name. It's entertainment. Okay. So it is at higher vapor velocity, droplets of liquid in the wick are torn from the wick and sent into the vapor. It also results in the dry out. So basically, the vapor velocity should not be very high. If they are very high, then what will happen? The liquid in the wick are torn from the wick and sent into the vapor. Other is sonic limit. So it is occurred when the vapor velocity reaches sonic speed at evaporator, and any increase in the pressure difference will not speed up the flow. Okay. So like choke flow in converting diverging nozzle and usually occurs during the startup of the heat pipe. So it is also a limit. So here we can see the vapor chambers. So here you can see the flattened profile. So there's a 2D heat transfer principle, okay, and same like principle as like heat pipes. So this is the heat in. These are evaporator, okay. This is the heat out. Here liquid in converting into the vapor. You can see this is in 2 dimension. So these are vapor chambers. Now micro heat pipes. So micro heat pipes are basically small heat pipes that are non-circular and use angled corners as liquid arteries and characterized by the equation Rc upon Rn, Rh greater than 1, where Rc is the capillary radius and Rh is the hydraulic radius of the flow channel. Employed in cooling semiconductors. For semiconductors, we are using like this micro heat pipes, okay, for improved thermal control, in also laser diodes, in photovoltaic cells and medical devices. You can see it's only 20 mm, very small length, 20 mm only. In this 20 mm, one side is evaporator, other is condenser, you can see. And you can see this is only 120 micrometer. It is very small. That's why it is micro heat pumps. Okay. So you can see the liquid and the vapor. So this is the micro heat operation. This is the side view. This is the end view. This is the heat input. It is heat output. Okay. And there is the thermosiphon. Is a physical effect and refers to a method of passive heat exchanger based on natural convection, which circulates a fluid without the necessity of mechanical pump. So it is a solar water heater. You can see directly. We can using solar radiation. We can heat the water. It's a very popular, and I think in various homes, homeowners have installed these on their roofs. So it can directly, like there is a water tank. Okay. So there is a cold water on the bottom side and hot water will be on the upper side. So the cold water is flowing in the through these tubes, and due to the sun rays, and there's a upper glass layer, so the heat will be trapped inside the this glass box, and that heat will heat the fluid through these tubes. Okay, and the hot water will flow again to the pump, and due to the heating, the hotter liquid is having slightly low density than the cold liquid. So hot water will be at the upper side and the cold water will be at the lower side. Okay, so again this cycle is completely flowing. Okay, so in this way you can see we are not using any pump or any external power source. This is also a passive type of heat exchanger. So this is also example for this. So today we have covered various question and theory, and still we have 10 minutes left. So maybe I can again go back from slide 1 to end, and if you are having any doubt in between, you can tell me, we can discuss. So the first question we have discussed about the heat pipes transport heat dominantly in, so it was 1D direction. We have also seen the theory about this. So the heat pipe act as it's passive heat transportation device, because heat pipe does not need external power to pump the condensate back to the evaporator, and hence it is passively operating device. Now, which of the following orientation of the heat pipe is referred to attain maximum performance? So we have discussed it. Due to the gravity and all, the pressure difference due to hydrostatic head assist pumping effect in moving the liquid from condenser to evaporator. So the correct answer is A. If you are having any doubt, the floor is open. We can have a discussion. The capillary pressure head must be greater than, it should be greater than the sum of liquid pressure drop in the wick pressure, vapor pressure drop and the hydrostatic pressure head. For more detail, you should refer to the class notes because there is a very big derivation on this. So it will be good if you go there and study them. How bends along the length of heat pipe impact functioning of heat pipe? So bends in the flow path will result in additional pressure drop, resulting in lower flow rate and power rating. So that the power rating will decrease or reduces. Which of the following are the features of vapor chamber? So the 2D heat dissipation is there. Similar working principle as heat pipe. Okay, and is also passively operating nature. So all of the above is correct. Which of the following generator generate power in thermoelectric generator? So we know that we have also discussed it. Like thermoelectric generator, there is no mechanical power involved. Okay, there is direct thermal to electrical conversion, and it is happening due to the Seebeck effect. Okay. So in thermoelectric device, the thermoelectric elements are connected to each other. So they are connected in series according to electrical connection and in parallel according to thermal connection. If the liquid mass flow rate is heat pipe is found to be, we have given the mass flow rate, we have to calculate the axial power rating, and we have to multiply the enthalpy with the flow rate. Okay, if we are changing it, we are reducing, so we know that they are connected with the proportional to density and inversely proportional to length and viscosity. In that way, after the calculation, it will come to 50%, so it will be double. So these are the basic components of heat pipe. Okay, condenser, evaporator, adiabatic section, the wick. This is a cycle, ideal thermodynamic cycle. These are the advantage of heat pipes: very high thermal conductivity in the mostly in axial direction, that is up to 10,000 watt per meter Kelvin, which is very high. They are light, reliable, and cheap, and means of transporting heat from point A, that is inconvenient location maybe, to point B, that can be a convenient location with minimum thermal resistance. This is again a diagram of a heat pipe. You can see on the left side there is heat in, on the right side there is heat out. There is a metal wick structure, there is a liquid flow, there is a vapor flow. So these are basically used for gas to gas heat recovery. You can see on the right side we are having hot waste gases. On the left side we are having cold air. So we can heat the cold air to heated air for our process heating. We can cool the hot waste gases to cooled waste gases. And in this way we can use the waste heat in the way. And you can see here we are installing multiple heat pipes to to maximum recovery of waste heat. We can also do the de-icing of the roads, okay, by using the underground heat of the earth crust. We can use heat pipes in like IC engines, in gas turbines. These are the wick structure like axial groven, screen, and sinter. So we can use in the laptops thermal design. CPU solution is also there. And there are some main heat transfer limitation in the heat pipes, that is capillary limit. So that occurs when the capillary pressure is too low to provide enough liquid to the evaporator from the condenser. It leads to dry out in the evaporator. Due to this, dry out prevents the thermodynamic cycle from continuing and the heat pipe no longer functions properly. Other is the boiling limit. It occurs when the radiation heat flux into the heat pipe causes the liquid in the wick to boil and evaporates, causing dry out. The third one is entertainment limit, that at higher vapor velocities, droplets of the liquid in the wick are torn from the wick and sent into the vapor. That also results in dry out and the heat, heat pipe will be fail. Then the sonic limit is there. This is the vapor chamber. So the difference is that it is same like heat pipe. The difference is that it is having a flattened profile, so it will be 2D. Okay? So the heat transfer will be in 2D direction, not in 1D. There are also micro heat pipes, very small, that can be used for semiconductor application, laser diodes, photovoltaic cells, and medical devices. Then is thermosiphon system. So I think it's enough for today's class. Anybody having any doubt? So I'm still available for 5 minutes. If you're having any doubt, let me know. I'm available here. Let me know if you have any doubt.
No doubts.
Okay. Okay, but still I'm here for 4 minutes. If you ask anything else, you can ask.
Sir,
Yeah.
sir, when we mix ice with salt, temperature goes in still in minus degrees, sir. Why, sir?
When we mix with the
Salt,
okay,
ice with salt, sir. Temperature goes in minus degree.
maybe then I think that these are the chemical reaction. I don't know the reaction, exact reaction. Maybe it will be release heat.
Hmm.
Maybe that's why it's going to, or it's going to lower in temperature, because the the salt will react with the liquid molecules and they will release heat very fast, and the temperature will further drop. So there will be an exothermic reaction, and if we can see that this is H2O and NaCl, sodium chloride. There will be some chemical reaction, you can Google it, yeah. I'm not remembering the exact reaction.
Okay, sir.
But the basic funda is saying that if the temperature is dropping, if you are adding these two, then there will be, for sure, there will be exothermic reaction. So it will release the heat, okay? And due to that, the temperature will further drop. No, I think it can be, I think, endothermic reaction. Because if it release heat, then ice will melt. It will take heat actually, maybe, from the water molecule. and in that way the temperature will drop. Yeah, I'm also confused about this. Confused about it. So you have to check it.
Yes, sir. Sir, if you know some word about it, tell to me by next week, sir. Anything.
Sorry.
Tell by next week some to me, sir. If you know something more about it.
Okay, okay, okay. It will be good. Yeah, for sure. Yeah. So next week we can discuss it. Yeah. Okay then. Thank you everyone for joining. I hope on next Friday we will meet again. Thank you. So I'm ending
Sir.
this class. Thank you.
Thank you, sir.